Good morning, class. Today's lesson is on topology, not to be confused with topography, although it does relate to maps in a way because it has to do with shapes of things and topological space. Let's begin with an overview. The overview. Topology offers the language of modern analysis and geometry. This lesson will focus on formalizing the notion of a shape, notions of closeness, and properties of topological shapes between spaces. Topology is a well-defined mathematical discipline that originated in the early part of the 20th century, but for some results can be traced back several centuries. Nowadays, topology provides the language of modern analysis and geometry. Topology is a very broad topic in mathematics and has many disciplines. Let's look at our objectives. Objectives. Understand who were the early contributors of topology. Understand what topology is. Understand what deformation means. Show examples of topology. Identify the different types of topology. After today's lesson, you will be able to understand who the contributors to topology were, what topology is, what deformation is. You will also see some examples of topology and know that there are different types of topology. Many mathematicians are credited with being the first to develop topology, depending on what books you read and what type of topology you are studying. Although this is the case, here are a few that made substantial contributions to the field of topology. Contributors to topology. First one is Johann Benedict Listing, 1802 to 1882, was the first to use the word topology. Leonhard Euler is considered the father of topology. Henry Poincaré defined the modern subject of algebraic topology at the end of the 19th century. Enrico Betti wrote a pioneering memo on topology that later led to the naming after him of the Betti numbers. Bernard Riemann contributed to analysis, number theory, and differential geometry. Topology is not interested in measurements of objects such as angle, length, and volume. It studies more basic shapes, properties. Topology studies the properties of space that are preserved under continuous deformations. What does deformation look like and what are the parameters? Question. What is topology? Topology is the study of shapes and spaces that do not change under deformation. It is referred to as the mathematics of continuity or theory of abstract topological spaces. A simple way to describe topology is as a rubber sheet geometry. In topology, as long as you do not cut, tear, or glue the original structure, any stretch, twist, bend of the deformation is accepted. To a topologist, a sphere and a bowl are the same, since you can deform one into the other. For example, a circle and a square are topological equivalent. Physically, a rubber band can be stretched into the form of either a circle or a square, as well as many other shapes which are also viewed as being topologically equivalent. If you have a rubber band, you can use it to form a circle, an ellipse, or a square. Those are very different shapes geometrically, but from the topological perspective, they are the same. Let me demonstrate. I have a rubber band in my hands. I'm going to demonstrate to you what I mean with this rubber band. Although I can twist it, it changes the shape by stretching it. In topology, it remains the same. What does deformation look like? The rule of deformation. Properties of space that are preserved under continuous deformations, such as stretching and bending, but not tearing or gluing. From the viewpoint of topology, they are all the same shape. If you turn the coffee mug into clay, you can remove it from the mug shape to donut shape without tearing it, or breaking it, or gluing any edges together. One can become the other by just squishing and stretching. So in topology, they are the same shape. And this slide is, are these shapes topologically the same? Give it a try. Well, yes, in topology, the exact shape doesn't matter. What matters is the basic continuities of the surface. What is connected to what points are close to what other points. Two objects that can be stretched into the same shape are described as homeomorphic, from Latinized Greek for similar to, homeo, and Greek form, shape, or figure, morphe. Through this lens, virtually all everyday objects are homeomorphic, with a sphere, example a ball, or some variety of torus, like a donut. Homeomorphic means similar shape. Virtually all everyday objects, when subjected to continuous deformation, reduce to just a few topological shapes. As you can see these examples of plates, trees, cubes, pants, shirts. Here is Euler's famous formula for a polyhedron formula, which is V minus E plus F equals 2, where V is the number of vertices of the polyhedron, E is the number of edges, and F is the number of faces. And below, you can see below an example of the torus polyhedron. And I have it on this slide. Euler's famous formula for a polyhedron, which is V minus E plus F equals 2, as I just stated, where V is the number of vertices of the polyhedron, E is the number of edges, and F is the number of faces. Below is an example of a torus polyhedron, as with all tori, the Euler characteristics F plus V minus E is 0. In this case, F equals 16, V equals 16, and E equals 32. To demonstrate an object's Euler's characteristics, first we take a sphere, or an object homeomorphic with a sphere, like a human head, a tile the surface with polygons. Then count the number of faces, sides, edges, places where two sides meet, and vertices, places where three or more sides meet. Next, add the number of faces, F, and the vertices, V, and subtract the number of edges, E, which we have F plus V minus E formula. It doesn't matter how you divide up the surface. The answer will always come out the same. 2. Since the 5 platonic solids, the 3D shapes made from one kind of regular polygon, are all homomorphic to a sphere, they also have a Euler characteristics of 2. Another example, another slide. Below are examples of homomorphic to a sphere and have a Euler characteristics of 2. And these 5 examples, which we have a tetrahedron, the cube, the octahedron, the dodecahedron, icosahedron. Here we see how algebraic topology considers the global properties of spaces and uses algebraic objects such as groups and rings to answer topological questions. Algebraic topology converts a topological problem into an algebraic problem that is hopefully easier to solve. The torus and the plane model can be distinguished from each other because they have different homology groups. To turn to the 2D surface of a fundamental polygon into a 3D object, stretch the surface so the corresponding sides join in the direction indicated by the arrows. Joining parallel sides makes a cylinder. E times C equals 0, and joining anti-parallel lines makes a Mobius strip. E times C equals 0. Edges labeled with letters are joined together in the direction indicated by the arrows. The dashed edges remain. Here we have the cylinder and the Mobius strip with the arrows pointing, the fundamental polygons of the cylinder and the Mobius strip. Let's move on to other types of topology. Yes, there are different types. Here you see metric topology, which is the study of distance, very important, in different spaces. The measure of distance and related concepts like angles in different topologies, and algebraic topology, the study of topologies using the tools of abstract algebra, in particular, studies of things like how to construct a complex space from simpler ones. Category theory is largely based on concepts that originated in algebraic topology. Here are some more types of topology. The one that I typically use, which is geometric topology, the study of manifolds and their embeddings. In general, geometric topology looks at lower dimensional structures, most either 2 or 3 dimensional. A manifold is an abstract space where every point is in a region that appears to be Euclidean if you only look at the local neighborhood. But on a larger scale, the Euclidean properties may disappear. Network topology is topology in the realm of discrete math. Network topologies are graphs. In the graphs, theories make sense, consisting of nodes and edges. And of course, the last one will be, and lastly, differential topology, the study of differential equations in topological spaces that have the properties necessary to make calculus work. Topology is important in today's world in the areas of theoretical physics. In particular, the successors of quantum mechanics, yes, quantum mechanics, such as quantum field theory and string theory. What about cosmology? For determining the shape of the universe, important also. Biology, yes, for the tangling of DNA and predicting the growth of organs and other body parts. Computer science, for determining the large-scale structure of data sets. And robotics, where robot arms be planned based on the shape of a space with a number of dimensional equal to the number of arm joints. Mathematicians will continue to participate in research, and there is no doubt they will discover new uses for different disciplines in mathematics and topology. Before I conclude, I would like to ask if anyone has a question that I can answer.
Yes, you just went through several different types of topology, and if I were interested in doing some research or studying further, which one of those topologies might you recommend?
Well, I will recommend, my opinion is geometric topology. It involves open and closed sets, and it goes into more of a math term than abstract math. Yes.
Thank you.
If you have any questions, I will be available after class, or you can email me with your questions. Thank you, class. Till next.